Welcome to this, the 8th lecture on the fundamentals of transport processes, and this is when we get down to business. We actually start solving problems on the temperature, velocity and concentration fields in simple situations. The simplest situation that one can consider is the example of the transfer between two flat plates. Okay. I have two flat plates separated by a distance L. Okay. And in the heat transfer problem, I will have a fluid of thermal conductivity K, okay, between the two plates, and I will keep the temperatures of the two plates at two different values, T naught and T 1. Okay. And then I want to know what is the temperature in between the two plates. Okay. In the case of steady state, it is quite easy, it is just a linear variation of temperature between the two plates. Okay. So, finally, at steady state, the temperature would be linear. Okay. It would start at T naught over here and go to T 1 over here. Okay. A linear variation in temperature. Okay. But that is not the only situation. I could have a situation where, for example, the entire system was at temperature T naught at the starting point, and I instantaneously supplied heat to the lower plate, so that the temperature at the lower plate became T 1. And then one can ask, what is the variation of temperature? Okay. Obviously, at very early times the temperature is going to be a constant throughout, okay. But then I have increased this temperature to T 1, and therefore, at early times I will have a variation that looks like this. Finally, in the long time limit it will go to a linear temperature gradient. Okay. So, we want to consider both steady and unsteady situations. Okay. The equivalent mass transfer problem is to have a medium between the two plates. Okay. The concentration on the lower one is C 1, the concentration of the upper one is C naught, okay. And I have a medium with some diffusion coefficient d, okay, separated by a length L. Okay. So, I have two porous plates, I fix the concentration on those two plates, and I want to find out what is the concentration in between. Okay. The momentum transfer problem is analogous to this one. Okay. So, I have two plates, okay. This is at 0 velocity, and I set this moving with a velocity u. Okay. And if I wait for sufficiently long, I will get a linear velocity profile between these two plates. Okay. And obviously, I have to calculate all of these temperature, concentration and velocity profiles, okay, the velocity fields, the variation with respect to position, okay, not only of the final state, but also of these transient states. Okay. So, as I said, explained in the introductory lectures, there are two things involved here. One is the balance laws. Okay. These balance laws are for mass, momentum, energy, okay, and those are written for a small differential volume. Basically, what they will tell you is how the concentration varies with location in a small differential volume. Okay. Once I have that, I now have to find out what is, because I am in the problem itself, I am not given the concentration variation at every point. I am only given the value at the two boundaries, okay, and I know what is the variation in each differential volume. From that, the form of the variation in each differential volume, I have to construct the total concentration, temperature, velocity fields across the entire system, and that involves a process of integration, as I told you. Okay. So, we will go through those two separate steps first in this lecture. Okay. So, first, how do we write a balance for a small differential volume? It is called a shell balance. Okay. And the volume has to be chosen in such a way that it corresponds to the symmetry of the configuration that we are considering. In this particular case, I have two infinite plates. Okay, these are, so I first thing is to choose a coordinate system that I can use to analyze the problem. In this particular case, I just have two flat plates, so I can choose a coordinate system as a Cartesian coordinate system x, y, and the distance between the plates is the z coordinate. Okay. And this location is z is equal to 0. This is at z is equal to capital L. Okay, so these are the two flat plates, okay, the boundaries of the domain I am considering. The plates themselves are considered to be infinite in the x y plane. Okay. So basically, these two plates are of infinite extent in the x and y directions, and there are two boundaries at z is equal to 0 and z is equal to L. Okay. So I prescribe a temperature T is equal to T naught here, and T is equal to T1 at the lower boundary. Okay. So that is what is given to me. Okay. How am I going to solve this problem? Okay. First, I consider a small differential volume. Okay. Between these two plates. Okay. This has extent delta x in the x coordinate, delta y in the y coordinate, and delta z in the z direction. Okay. Since the system is of infinite extent in the x y plane, there will be no variations of the temperature in the x and y directions. So, the temperature is a constant in both the x and y directions, and it is only a function of the z coordinate. Okay. If it is at steady state, it is not a function of time. For the general unsteady problem, the temperature will also be a function of time as well as the z coordinate. Okay. So, let us try to derive an equation for the temperature which tells us how the temperature will vary with respect to the z coordinate as well as with respect to time. The fundamental principle here is the energy conservation principle. Okay. So, the energy conservation principle states that the change in energy in a small time delta t within this volume, okay, within this volume, the change in energy within a small time delta t is going to be equal to energy in minus the energy out. Okay. So, this is the fundamental principle, okay, plus any sources or any sinks, okay, minus sink. Okay. The sources could be due to an exothermic reaction, the sink could be due to an endothermic reaction. For the present, we will not concern ourselves with the sources and sinks. Okay, we will assume that there is no heat generation or absorption within the fluid, and therefore, we only have the transport of energy, okay, across the surfaces of this differential volume. Okay. What is the change in energy in a time delta t? Okay. The change in energy in the time delta t is equal to this is equal to the energy per unit volume, okay, specific energy times the volume. Okay. So, this is equal to the specific energy times the volume, which is delta x, delta y, delta z at time t, okay, at the time t, okay, change in energy. Okay. I should be careful here. This is energy at time t. Okay. Energy at t plus delta t will be equal to E times delta x, delta y, delta z at t plus delta t. Okay. Therefore, change in energy will be equal to E at x, y, z t plus delta t minus E at t times delta x, delta y, delta z. So, that is the change in energy within the time interval delta t. Okay. This specific energy, I can also write it as the density times the specific heat times temperature. Okay. So, this can also be written as rho Cp times T at x, y, z t plus delta t minus rho Cp T at x, y, z t times y delta z. Okay. So, that is the change in energy, okay, within this differential volume. Okay. What is the energy in? Okay. So, if we consider the plus z coordinate, okay, the heat flux upward as positive, right, then the energy in is coming in at this bottom plane. The energy is coming in at this bottom plane z. Okay. So, energy in, okay, is going to be equal to the flux in the z direction at the location z. Okay, the flux at the location z. Flux is energy per unit area per unit time. Okay. So, the total energy in has to be flux times the area times the time interval. Okay. So, the total energy in has to be flux times delta x, delta y, that is the area of that bottom surface, times the time. So, that is the flux in. Okay. Flux qz has been defined positive if it is acting in the upward direction. Okay. So, the flux qz is positive if it is in the plus z direction. Okay. What is the energy out? Okay. Okay. The energy that is going out at the upper surface. Okay. The upper surface is at the location z plus delta z. Okay. Therefore, energy out is equal to qz at z plus delta z times delta x, delta y, delta t. Okay. So, this gives me the energy in and the energy out. Okay. So, change in energy within a time delta t has got to be equal to the energy in minus the energy out. Okay. Change in energy in a time delta t, okay, rho Cp T at x, y, z t plus delta t. I am assuming for the moment that the density and the specific heat are not functions of position. The temperature is the only variable that is varying with position. Okay. Okay. This multiplied by the volume. Okay. This is equal to flux in, the energy in, which is equal to qz at z times the area, cross sectional area perpendicular to the z axis, the cross sectional area times time, okay, minus the energy going out of the top surface, okay, qz at z plus delta z times delta x, delta y, delta t. Okay. Now, divide by delta x, delta y, delta z, delta t. Okay. Dividing by the volume and by the time interval. Okay. Once you do this division, what you will get is that rho Cp into T at x, y, z t plus delta t minus T at x, y, z t, the whole thing divided by delta t, okay, is equal to Qz at the location z minus Qz at z plus delta z by delta z. I can now rewrite this equation a little bit. Okay. On the right hand side, I can write this as minus of Qz at z plus delta z minus Qz at z divided by delta z. Okay. And I take the limit delta t going to 0 and delta z going to 0. Okay, I take the limit of both delta t going to 0 and delta z going to 0, and my final equation becomes rho Cp partial t by partial t is equal to minus . Note that I have here these partial signs. Okay. When you take the partial derivative with respect to time, as indicated over here, you are keeping the positions a constant, x, y and z are a constant. You are taking the limit as delta x, delta y, delta z go to 0, right. But when you take the partial derivative, you are keeping x, y, z a constant. When you take the partial derivative with respect to z, I keep the other independent variables a constant. In other words, I am keeping x, y and t a constant. Okay. So, this equation basically tells me how the temperature changes due to the flux through the system. Okay. In order to get an equation for the temperature alone, I need to have some way of calculating the flux in terms of the temperature, and that is where the Fourier's law for heat conduction comes in. Okay. So, if I have two surfaces, okay, okay, separated by a distance delta z, okay, this is T at z plus delta z and this is T at z. Okay. The flux, okay, in the z direction is equal to minus k into T at z plus delta z minus T at z by delta z. Okay. This was for one dimension. Okay. The same thing holds for variations in time as well, because the heat energy always goes from a higher temperature to a lower temperature. Okay. The flux at time z plus delta z, the temperature at time at position z plus delta z, if it is higher than at z, then the flux will be downwards. Okay. And that is the reason for the negative sign. If I take the limit as delta z goes to 0, okay, this basically becomes equal to minus k dt by dz. Okay. Once again the partial derivative, I am taking the variation of temperature, keeping with respect to the z coordinate, keeping x, y and t a constant. Okay. So, once I have that, if I insert this into the previous equation, okay, rho Cp partial t by partial t is equal to minus partial Qz by partial z, which is minus partial by partial z of minus k dt by dz. Okay, it is equal to minus k d square t by dz square. Assuming here that the thermal conductivity is not a function of position. So, you have a material or a fluid with a constant thermal conductivity. Okay. This is the diffusion equation for, I am sorry, there should be no negative sign here. Let me take that out. Yeah. Okay. This is the diffusion equation for heat. Okay. I could divide by rho Cp and I will get dt by dt is equal to alpha d square t by dz square, where alpha is equal to thermal diffusivity. Okay. So, this is the diffusion equation unsteady that you would use for solving one dimensional problems, okay, for the variations of the temperature. Okay. How about the concentration diffusion? I will not go through this concentration diffusion equation in very much detail, because the method for deriving it is very similar to the method for thermal diffusion equation. Okay. I have two plates, okay, separated by a distance L. Okay. C is equal to C naught on the top plate, C is equal to C1. Okay. And because of the difference in concentration, there is a flux of mass going upwards. And what we would like to do is to determine the entire concentration field. First things first, we choose a coordinate system. Okay. Once again, x, y in the z coordinate. The planes are infinite in the x, y plane. Okay. So, there is no variation within the x, y plane. There is a variation only in the z direction. There could be a variation in time as well. Okay. So, once again we take a small differential equation, differential volume, okay, the shell balance, okay, between the location z and z plus delta z. Okay. Okay, of height delta z and thickness delta x and delta y in the two directions. Okay. The basic principle in this case is the mass conservation principle. Okay. That is, change in mass in time delta t is equal to mass in minus mass out. Okay. There could be sources and sinks of mass as well. Okay. For example, I could have a reaction taking place which is generating some species, some product species, and consuming the reactants, in which case the concentration will have sources and sinks in it. For the moment, let us not consider that. Okay. Let us just consider a case where the mass itself is conserved and there are no reactions taking place. Okay. Change in mass in time t. Okay. The mass within this volume is going to be equal to the concentration times the volume. So, the mass at time t plus delta t is going to be equal to the concentration at x, y, z t plus delta t times the volume. The volume is delta x, delta y, delta z. Okay. That is the mass at time t plus delta t. Change in mass is equal to the mass at time t plus delta t minus the mass at times t. Okay. So, this minus the concentration x, y, z t times delta x, delta y, delta z. Okay. So, if I consider two time intervals separated by a small delta t, then the change in mass within the time interval has to be equal to the concentration times the volume at time t plus delta t minus the concentration times the volume at time t. Okay. What about the mass in and the mass out? Okay. The mass in mass n is because of the flux that is travelling vertically along the z coordinate. Okay. We assume that flux in the positive z direction is positive. So, mass that comes in has to travel into the volume at the location z. Okay. So, mass n is going to be equal to the flux at location z. Okay. Flux is mass transported per unit area per unit time. So, I have to multiply that by the cross sectional area of that bottom surface. Cross sectional area of the bottom surface delta x, delta y, and the time interval delta t. Okay. So, that is the mass n at the bottom surface. okay, at location x, y and z. Okay. Mass out at the top surface, okay, that is going to be equal to the heat flux at the top surface times the area times time. So, this is going to be equal to J z at z plus delta z, delta x, delta y, delta t. Okay. So, now I have the three different terms together, okay, mass in and mass out, and I now put them all three together to get the conservation equation. Okay. So, the conservation equation will be of the form C at x, y, z, t plus delta t minus C at x, y, z, t, okay, into the volume delta x, delta y, delta z is equal to mass in within the time interval delta t. Mass in is J z times at the location z times delta x, delta y, delta t, okay, minus J z at z plus delta z. Okay. The complete form of the mass conservation equation for that differential volume. Okay. Divide throughout by volume and time. Okay. Divide by delta x, delta y, delta z, delta t. So, I will get C at x, y, z, t plus delta t minus C at x, y, z, t whole divided by delta t is equal to J z at the location z minus J z at z plus delta z divided by delta z. Okay. Once again, I can rewrite the right hand side slightly as minus of J z at z plus delta z minus J z at z by delta z. Okay. Take the limit delta t going to 0, delta z going to 0. Okay. This becomes partial c by partial t is equal to minus d j z by d z. So, this is the mass conservation equation in terms of the mass flux. Okay. Now, to close the equation, we have to now write the mass flux in terms of the concentration. Okay. And the mass flux in terms of the concentration is quite easy. We have done it before. J z is equal to minus d times partial c by partial z. Okay. Just as in the case of heat flux, q was equal to minus k times dt dz. Okay. In this case, J z is minus d times partial c by partial z. Okay. And with this, I have the mass conservation equation partial square c by partial z square. Okay. So, this is the unsteady diffusion equation for the concentration field. Okay. You will notice that both the equations for the temperature and the concentration field had the form d by dt of concentration temperature is equal to a diffusivity times d square by dz square. Okay. Dimensionally, it makes perfect sense because d has dimensions of length square per unit time. Okay. So, this is a standard diffusion equation in one dimension. Okay. We will see a little later how it changes when we go to higher dimensions. Okay. So, we have to solve either the concentration equation or the temperature equation, the diffusion equation for either one of them in a finite domain bounded by two walls separated by a distance L. Okay. So, we have done mass and momentum. Okay. What about, I am sorry, we have done mass and energy diffusion. Okay. What about momentum diffusion? The fundamental balance law for momentum diffusion is slightly different. So, I will try to go through it in some detail. Okay. The configuration typically consists of two plates. Okay. I move the bottom plate with the velocity u. Okay. The top plate is stationary. So, the velocity is equal to u here and ux is equal to 0 on the top plate. Okay. At steady state, I will have a linear velocity profile. Okay. Let us use a Cartesian coordinate system as before, where x and y coordinates are in the plane of the plates and z is perpendicular to the plates, the distance between the two. In this case, okay, this z is equal to 0 and z equals L. Okay. So, we use a Cartesian coordinate system as before, x, y and the z coordinate. The balance condition for momentum which we use is slightly different. Okay. The balance condition is that the rate of change of momentum is equal to sum of applied forces. Okay, this is the same as Newton's. This is what comes out of Newton's laws of motion. Okay. Rate of change of momentum is equal to sum of applied forces. Important point to note here, momentum itself is a vector. It has a direction to it. In this particular case, the fluid velocity is in the x direction, which means that the momentum vector is along the x direction. Okay. However, along the x direction nothing changes. Okay. So, if I travel along the x direction, okay, keeping z a constant, there is no change in velocity. At every location along the x, as I change the x coordinate, at every location the velocity is the same. Okay. So, even though the velocity vector is in the x direction, it does not change in the x direction. Okay. Momentum transport takes place along the direction where there is a change in velocity. In this particular case, the velocity changes only in the z direction. Okay. It does not change along the x direction. Therefore, momentum transfer takes place only along the z direction. Okay. So, rate of change of momentum is equal to sum of applied forces. Okay. So, that is a fundamental balance law. In this case, as I said, momentum is along the x direction, change in momentum is along the z direction. Therefore, the transfer of momentum, the flux of momentum is also along the z direction. There is no change in any quantities along the x direction. We will take our usual differential volume. Okay. This is z plus delta z. Okay. So, the differential volume is bounded by z and z plus delta z, and then along the x and y directions, okay, the intervals are delta x and delta y. Okay. So, this is the configuration that we are considering. Okay. What is the rate of change of momentum? Okay. The momentum, okay, in the volume delta x, delta y, delta z. Okay. What is the momentum within that volume? This is equal to the density times ux, okay, at x, y, z times the volume. Okay. Rho times ux, okay, rho is a mass per unit volume. So, rho times ux gives me a momentum per unit volume. I multiply that by the volume to get the total momentum. Okay. So, that is the basic principle. Okay. So, rate of change of momentum, change in momentum per unit time. Okay. So, if I look at two instances t and t plus delta t, okay, the rate of change of momentum will be equal to rho times ux at x, y, z t plus delta t, okay, minus rho ux at x, y, z t. Okay. divided by delta t times delta x, delta y, delta z. Okay. The rate of change of momentum in this volume, change in momentum per unit time, rho at ux, rho ux at x, y, z t plus delta t minus rho ux at x, y, z t times delta x, delta y, delta z, the whole thing divided by delta t. Okay. So, that is the rate of change of momentum, okay, within this differential volume. Okay. What about the sum of forces? Okay. We have to be a little bit careful here in how we define things as far as the sum of forces is concerned. Okay. So, I have some differential volume, okay, and there is a shear stress acting on the bottom surface as well as on the top surface. Okay. There are shear stresses acting on both surfaces. Okay. The shear stress, okay, tau x z, is defined as the force per area in the x direction acting at a surface with unit normal in z direction. The unit normal is the unit vector perpendicular to surface. So, the unit normal is the unit vector perpendicular to the surface. So, tau x z is the force per unit area in the x direction acting at a surface with unit normal in the z direction. Rate of change of momentum is equal to sum of applied forces. Okay. In this particular case, momentum is in the x direction because it is the x component of the momentum, rho ux. So, the momentum is in the x direction. Okay. I want the force on the top surface for my momentum balance equation. For the top surface, the unit normal is in the plus z direction. Okay. Therefore, the force on the top surface has got to be equal to the shear stress times the area of the top surface. Okay. I define tau x z as a force in the x direction. We are interested in momentum change in x direction. So, it is appropriate to consider the force in the x direction. Okay. Acting at a surface whose unit normal is in the plus z direction. So, this force on the top surface has to be equal to tau x z into the area of the top surface, okay, delta x, delta z, delta x, delta y. Okay. Except that this force is now acting on the top surface. On the top surface, the location is z plus delta z. Okay. The bottom surface was at z. Okay. So, this is tau x z at z plus delta z at the location x plus delta z, z plus delta z. Okay. Now, if you look at the bottom surface, okay, if you look at the bottom surface, the unit normal is in the minus z direction. Okay, the unit normal is in the minus z direction. Okay. Therefore, tau x z was defined as the force per unit area in the x direction acting at a surface whose unit normal is in the plus z direction. Okay. If the unit normal is in the minus z direction, the force will be opposite. Okay. Because of Newton's third law, which states that if I have at a surface, forces on both sides have to be equal and opposite to each other. Okay. The balance of action and reaction. Okay. For the top surface, the outward unit normal is in this direction, okay, whereas for the bottom surface, it is in the opposite direction. Okay. When I go from top to bottom, the direction of the unit normal changes and the direction of the force changes by Newton's third law. Okay. Therefore, the force on the bottom surface, whose unit normal is in the minus z direction, is equal to minus tau x z at z times delta x delta y. To repeat the principle once again, I have defined tau x z as the force per unit area in the x direction acting at a surface whose unit normal is in the z direction. Tau x z is the appropriate force to use because I am writing a balance equation for the momentum, and the momentum is in the x direction. When I look at the top surface, the outward unit normal, I should write outward, and this is important. This outward is important. Outward unit normal to the volume. The unit normal that acts outward from the volume. If I look at the top surface, the outward unit normal is in the plus z direction. Therefore, the force on the top surface is equal to the shear stress there times the area, tau x z at z plus delta z times delta x delta y. The opposite surface is the downward surface. Force on the bottom surface. The outward unit normal to the bottom surface is in the minus z direction. When I go from above the surface to below the surface, the direction of the unit normal changes, and from Newton's third law, the forces have to be opposite to each other. That means that the force acting on this bottom surface is minus tau x z at z times delta x delta y. So, we put all of that together. The rate of change of momentum, rho ux at x y z t plus delta t minus rho ux at x y z t divided by delta t into the volume delta x delta y delta z. This thing has got to be equal to tau x z at z plus delta z times delta x delta y, force on the top surface. On the bottom surface, the unit normal is in the minus z direction. The bottom surface, the unit normal is in the minus z direction. So, this is the balance equation. You divide throughout by delta x delta y delta z, and you will get rho ux at x y z t plus delta t minus rho ux at x y z t, whole thing divided by delta t is equal to tau x z at z plus delta z minus tau x z at z divided by delta z. Now, once again I take the limit of delta t and delta z going to 0, and my equation becomes d of rho ux by dt is equal to partial tau x z by partial z. If the density is a constant, it is not a function of time or of position, this equation can be rewritten as rho partial ux by partial t is equal to partial tau x z by partial z. Good. Now, I need to write the shear stress in terms of the velocity, and for that I use Newton's law for viscosity. Basically, Newton's law for viscosity states that if I have two plates moving with velocity ux at z plus delta z and ux at z, so there is a linear variation in velocity between these two plates, then the shear stress tau xz is equal to the viscosity times delta ux by delta z. Okay. The change in velocity divided by the separation of the two locations. Take the limit as delta z goes to 0, you will get this as mu times d ux by dz. Okay. So, put that into this differential equation, okay, and you will get rho times dux by dt is equal to d by dz of mu dux by dz. Okay. And if the viscosity is not a function of position, if we have a fluid with a constant viscosity, this can also be written as mu times d square ux by dz square. Okay. This is the diffusion equation for momentum in this case, except one should note that momentum is a vector, it has a direction associated with it. I can divide both sides by the density to get dux by dt is equal to mu by rho times partial square ux by partial z square, okay, which is just the kinematic viscosity times partial square ux by partial z square. And this kinematic viscosity is the momentum diffusivity for this particular problem. Okay. We used a slightly different methodology for momentum transfer as compared to heat and mass transfer. Okay. The reason was that for heat and mass transfer, the flux into a differential volume is considered positive, okay, and therefore we got equations of the form dc dt is equal to minus djz by dz, whereas in this case we had defined the stress to be positive if it is defined with respect to the outward unit normal. Okay. So, we do not have the negative sign in the constitutive relation. However, when we put that in to the balance equation, we still get an equation of the same form. Okay. So, for all of my for all my situations, I have common equations. Okay. For this case, I have dt by dt is equal to alpha d square t by dz square. Okay. In this case, I have dc dt is equal to the diffusion coefficient d square c by dz square. Okay. In this case, I have dux by dt is equal to the kinematic viscosity d square ux by dz square. Form of the equations is the same in all cases, shows the equivalence of heat, mass and momentum transfer. Okay. At steady state, the time derivatives are all 0. Okay. At steady state, the time derivatives are all 0. Okay. So, okay. Steady state, the equations here will become d square t by dz square is equal to 0, d square c by dz square is equal to 0, and d square ux by dz square is equal to 0. Okay. So, you can solve any of the equations equivalently, in order to get the steady state profiles. Okay. However, we will use one thing that will be useful later on when we do other kinds of transport problems. Rather than solving these equations directly, we will scale them. Okay. There is a temperature scale because the temperature varies between T1 at the bottom and T0 at the top. Okay. So, if I define a scale temperature, okay, if I define a scale temperature T star, okay, is equal to T minus T0 by T1 minus T0. Okay, if I define T star is equal to T minus T0 by T1 minus T0, okay, this is a scale temperature. Okay. In that case, at the bottom surface, I will have T star is equal to 1, okay, because T is equal to T1, so T star is equal to 1. At the top surface, I will have T star is equal to 0. Okay. So, the scale temperature varies approximately between 1 and 0, okay, in all three cases. Okay. I could define a scaled length, okay, z star is equal to z by L. Okay. In that case, z star varies from 0 at the bottom to 1 at the top. Okay. In the case of concentration field, I could define C star is equal to C minus C naught by C 1 minus C naught. Okay. That means that at the bottom C star is equal to 1 and the top C star is equal to 0. Okay. Once again, at the bottom Z star is equal to 0 and Z star is equal to 1. Okay. In the case of the momentum conservation problem, okay, I could define a scaled velocity ux star is equal to ux by u, okay, in which case ux star is equal to 1 at the bottom and is equal to 0 on top. When defined in terms of scaled quantities, the temperature, concentration and velocity in scaled form have identical values on the top and bottom plates. Okay. The scaled distance also has identical values. Okay. Therefore, the solutions will be identical. In scaled form, the solutions will be identical. Okay. The solution for all three cases will be T star is equal to C star is equal to ux star is equal to, it has to vary between 0 and 1, 0 at z equal to 1 and 1 at z equal to 0. Okay. And it has to be linear because the second derivative was 0. Okay. The differential equation in all cases was d square t by dz square is equal to 0. Even if I expressed it in scaled form, I would still get d square t star by dz square is equal to 0. Okay. In scaled form, you divide t by t1 minus t naught and z by L, and you will get the same differential equation in scaled form. That means that t star, c star and ux star have to be linear functions of position. Okay. And you can easily verify that the linear function that satisfies this is 1 minus z star. Okay. So, that is the solution of the equation. Okay. It is exactly the same at steady state for all three cases. Okay. Once I have expressed it in terms of scaled variables. Okay. And the scaling is a useful concept, okay, because for example, I could have a real temperature between these two plates varying between say 20 degrees and 40 degrees centigrade. Okay. But rather than represent it on a scale going all the way from 0 to 100, I could focus on the range that I am interested in, because the temperature range that I am interested in is only between 20 and 40. Okay. So, I do not have to look at it in an absolute scale. I look at it in a scaled variable where 20 is equal to 0 and 40 is equal to 1. Okay. So, it varies between 0 and 1. Okay. So, that takes into account the scaling for the variation of the temperature. Okay. Once you scale these temperature fields, concentration fields and velocity fields in this way, it takes into account the real variation across this distance. And similarly, z could vary from 1 meter, 1 centimeter and so on. Okay. But what really matters is the length scale for the plates itself. Okay. And so, if I scale it by the distance, okay, then I will just get one boundary to be at 0, the other boundary to be at 1. Okay. And that scaling will turn out to be a very important concept in the course that we, as we go along. Okay. So, I derived for you the conservation equations for unidirectional transport, mass, momentum and energy. They all have identical forms. In the case of mass conservation, you have the mass diffusion coefficient. Momentum conservation, there is the thermal diffusivity alpha. In the case of energy conservation, there is the thermal diffusivity alpha. Momentum conservation, there is the kinematic viscosity or the momentum diffusivity, which is the ratio of viscosity and density. Okay. Once expressed in this form, all three equations have identical forms. Okay. And one could work with the form of the differential equation, which is of the form dc by dt is equal to some diffusivity times d squared c by dz square. Okay. And one has to solve that problem subject to the conditions on the two surfaces as well as the conditions at the initial time. Okay. So, these all three equations which I got here. Okay. This equation, for example, is the first order differential in time, differential equation in time, second order differential equation in Z. You need two boundary conditions in Z. For example, in the problem that we took, the two boundary conditions are at the two plates, okay, Z is equal to 0 and Z is equal to L, but you need two boundary conditions in Z, and since it is first order in time, you also need an initial condition. Okay. We have first considered the simplest case where it is at steady state. So, there is no variation in time. Okay. Then d square T by dz square is equal to 0, temperature is just a linear function of Z, easy to solve. I introduced the concept of scaling just to just so that you can be aware of it at this point. Okay. Next class we will look at other unsteady problems. Okay. We will look specifically at this case where you start off, okay, from the whole fluid is at a constant temperature, instantaneously you heat up the bottom to a higher temperature. How does the temperature field evolve within the fluid? Okay. Equivalent concentration field at time t is equal to 0, you introduce some solute on the bottom plate and that diffuses across. How does it vary with time? Momentum conservation equation. You instantaneously impart a velocity in the x direction to the bottom plate. Okay. How does the fluid velocity vary as a function of time? Okay. So, initially it will look something like this, at later times it will look something like this, and finally it will converge to a linear profile. Those time dependent problems we will consider in the next class. Okay. We will spend some time on this unsteady diffusion problems, and we will also look at oscillatory diffusion problems. Okay. And after that we will go on to looking at more complicated problems in other types of geometries, cylindrical, spherical geometries and so on. Okay. So, I have derived for you the unsteady conservation equations here, turn out to be of the same form for mass, momentum and energy. I showed you how to solve it at steady state, turned out to be an ordinary differential equation, okay, because we do not have any variations in time. We will take up next class the more difficult task of solving the partial differential equations when there is a variation in time, and we will look at different ways of doing that. So, we will see you next time.